Hey, what's going on guys? Tanmay here. Welcome back to another video tutorial on data structures and algorithms. In this video, we're going to take an introductory look at M-way tree, also known as multi-way tree, and M-way search tree. Okay, so these are the two different types of trees that we're going to understand. Now, in case if you've missed any of the previous videos in this DSA playlist, we've covered the topic of trees, we've covered binary tree, we've covered binary search tree, we've covered AVL tree, balancing and whatnot. Please make sure you watch all those videos in the proper order of that playlist so that you can better understand this topic. There are going to be some references being made to binary tree and binary search tree. We're going to try to compare it with these two types of trees over here for understanding. So it's better that you watch those videos and have a good understanding of those trees first. I'm assuming you guys already know all that. With that being said, let's start off with today's tutorial. Let's start off with understanding what is M-way tree. Now, M-way tree is also called as multi-way tree, okay, and here's the definition. So, a multi-way tree is a tree that can have more than two children, okay. So, basically, in a binary tree, what we had is we had one node and it could have at most of two children, right? You cannot have a third child. But in multi-way tree, as the name suggests, this tree can have more than two children, okay. So a multi-way tree of order M or a M-way tree basically is a tree which can have M children. So if M is 3, it would be a 3-way tree, correct? In that case, it would have 3 children, kind of like this one. Now, as with other trees like binary tree, AVL tree and whatnot, the nodes in a M-way tree will be made up of key fields, and in this case, the number of key fields in one particular node is given by m-1. So do note this particular aspect of multi-way tree. So it will have m-1 key fields and m pointers to children. Okay. If this is confusing, let's just actually go to this diagram. But before we jump to this diagram, keep a note of this green line because this is very important. And that is, why do you actually need M-way tree or multi-way trees, right? What is the advantage or what is the difference between a multi-way tree and our regular binary trees? So the biggest advantage of M-way tree over binary tree is the short height and fast access of nodes. So less traversal overhead. Okay. We will understand these terms again when I do the comparison, but just for noting purpose, you can note this particular aspect of M-way trees and also the definition if you want. Okay, so let's take a look at this example. It does look huge and enormous, but we'll try to break it down. It's pretty easy once we understand it step by step and once we break it down. Okay, so this is a M-way tree. This whole structure is basically a M-way tree where M equals to 4, which means that every node can have 4 children, a maximum of 4 children. Okay. It can have 0 children also, it can have 1 child, it can have 2 children, 3 children and maximum of 4. And the keys inside that node is m-1, which is 3. Okay. Now a key point to remember over here is, unlike binary trees, in a binary tree, we only had one value, right? Let's say we have a binary search tree. So in a binary search tree, what we had is a parent node which will have only one key value, which is, let's say this is 13. Then it will have 2 children. Each of this children or each of this child will only have one single key. But in a multi-way key, in a M-way key, inside a particular node, we can also have multiple keys. Okay. And that number is given by this M value itself. We have to subtract 1 from the M value. So if the multi-way key is M equals to 4, the maximum number of keys it can hold is 3. Okay. So do keep this in mind. So let's take a look at this node. So this node is basically represented by this whole pink box. The name of this node is N1. This yellow text that is #FE in this brackets is nothing but a memory location. Ultimately, when you write program or ultimately in the practical reality, these nodes are going to be created in the computer memory. The computer memory has some digital address. So we are assuming that this node N1 is at this fictitious address #FE. Fictitious means we are just assuming this as a random address. It's not a real address. Okay. So name is N1. This is the address. And at this address, we have this memory location allocated to this node N1. Inside this node, you can see we have 3 keys, 65, 43, 75. because this is a M-way key where m equals to 4, it can hold maximum 3 keys. Okay. Along with 3 keys, it also has 4 pointers over here. Why does it have 4 pointers? You can see each of this pointer is storing an address #2e, #a3, #x4, #q2. Again, all these values are random address values which we have just assumed. They are not real addresses, okay? But they are basically addresses of 4 more nodes which this one node can point to. So N1 is the parent of 4 more nodes. Because this is an M-way tree, as I said, it can point to 4 more nodes, and those 4 nodes are N2 whose address is #2e. That's why it is stored over here. You can see #2e. Then we have N3 which is stored at our address location #A3 which is stored over here. Then we have X4 for N4. We have #Q2 for N5, right? Okay. The next thing is, let's take a look at this node. In this node, you can see we don't have 3 keys. We only have 2 keys, and that's fine. It can have 1 key also. It can have 2 key also. It can have 3 key also. It just has to be maximum of m-1, which in this case is 4 minus 1, which is equal to 3. Okay. So over here we only have 2 keys. Again, it is pointing to 2 more child nodes. It could have pointed to more 2 nodes over here with more 2 addresses stored in these pointers, right? But this is just for representation purpose, and this is a general M-way key, okay? This is not a M-way search tree. We'll come to M-way search tree in a minute, but I'm just trying to explain you, or just trying to showcase you the structure of how a M-way tree would look like and how it would look like in a memory if it had some addresses as well. So I hope the structure is clear. And there is one last formula, is that the maximum elements, or essentially the elements, is nothing but we are talking about the number of keys itself, okay? So these keys is what we are talking about when we say elements. So the maximum number of elements in a M-way key is given by this formula, m raised to h plus 1 minus 1. So h is nothing but the height of the tree, and m is nothing but the degree that we assume. So if we were to substitute the values over here in this particular example, m is 4. So 4 raised to, what is the height of the tree? I hope you know what is the height of a tree. Height is basically the longest path from the root node to a leaf node, and over here the height is basically 2. Okay, so 2 plus 1 minus 1. So 4 raised to 3 minus 1. So 4 cube is nothing but 64. 64 minus 1 is gonna give you 63. So if you are wondering how come we are getting such a high value, each of this node can store 3 keys, that is 3 elements, right? So for the first level, if you were to actually calculate for the first node or the first level, that is this root level, we have 3 elements maximum. So let's write over here 3 plus, let's come at this second level. Over here we could have had maximum 3 elements, 3. Over here again we could have had maximum elements, 3. Over here we could have had maximum elements, 3, and over here we already have 3. So 3 plus 3 plus 3 plus 3, which is equal to 12. Okay, so 3 plus 12. Now let's come at this level. Over here again we could have had 3 elements. Over here we could have had 3 elements. Over here we could have had 3 elements. Now do remember there are 2 empty pointers over here, which means we could have had more 2 children with 3 elements each, right? So I'll write 3 over here, I'll write 3 over here. Let me write 3 over here and 3 over here. Similarly, 3 elements in this node, 3 elements in this node, and 3 elements and 3 elements more if we had more 2 nodes, correct? Again, this node is not pointing to any more children node, but each of them could have had 3 nodes or 3 elements each, correct? And then for this last node, it has 4 children which each have 3 elements. So now if you take a big total, it's going to be, for this one particular node, it can have 4 children, and 4 children can hold 3 elements each, which means 4 3s are 12. So again, plus 12. For this node, it can have 4 children. Each children can have 3 elements each. So 4 3s are again 12. For this node also, it can have 4 children which each can hold 3 elements, and for this node also again 12, right? So if you take a total of this whole expression that we got, you will ultimately get 63, okay? So this is how you are going to get 63 elements which are the maximum number of elements, basically keys. Okay, we are talking about keys itself over here. Elements is nothing but keys that can be stored in a M-way tree of this height, okay, which is 2, and the degree of this tree is 4. Okay, alright, so do keep a note of this formula. Okay, so now that we've understood the structure of M-way tree and how it looks like and what it is, the next obvious question is, well, how beneficial is it and how can we use it? So in general, a generalized M-way tree is not really used or cannot really be used in practical purposes. Now if you observe this diagram, this is a general M-way tree. The keys are arranged in some random order, right? So you cannot see any specific order of arrangement of these keys. You can see 65 is over here, 43 is in the middle, 75 is at the end. On the left hand side we have higher values, on the right hand side we have smaller values. So there is no particular order to it. So there is no point or there is no use of this M-way tree if we use it in a generalized way. So just like a binary tree, it is just the structure, but when you actually add some conditions onto it and make it a binary search tree, that is when it becomes useful, right? So I hope you know the difference between binary tree and binary search tree. Just to give you a quick understanding or a quick reference of it, this is how a binary search tree is. A binary search tree is a tree data structure in which the values in the left subtree of every node are smaller and the values in the right subtree of every node are larger. So this is a general binary tree which is not really of any use in practical scenarios. If you're storing data in a binary tree, how are you going to find 52, right? If you want to find 52 in a regular binary tree, you'll have to go search this node, then you'll have to go search this node, you have to go search this node, then come back again, go to the right, go to the left, go to the right, and apply some kind of traversal. But in a binary search tree, if you want to search for 52, you know that 52 is greater than 25, so you know you have to go to the right. Again you'll come over here, you know 52 is again greater than 36, you have to go to the right, and that's where you find the number, right? So that's why binary search tree is more efficient in searching, because there is some rule applied to a regular binary tree and you convert it to a binary search tree. Now similarly, with the same context, a M-way tree can be more useful and we can make it a M-way search tree when you actually apply certain more conditions. So let's see what are those conditions. So this is a M-way search tree. Now these are the same values that we just saw in the M-way tree. If you want, you can scroll back this video and see the numbers. The numbers are arranged differently in this M-way search tree compared to the M-way tree, but that's the only difference. Otherwise the structure is more or less the same, but the M-way search tree has some extra properties. So let's go through them and let's try to understand what is different. So as I said, to make the processing of M-way tree easier, some type of order will be imposed on the keys with each node, resulting in a multi-way search tree of order M. So this is how you convert a M-way tree, a general M-way tree, to a M-way search tree, by imposing some type of order, that is some set of rules to make it better in terms of searching. So by definition, an M-way search tree is actually a M-way tree which has these 4 properties. What are these properties? Each node has maximum of M children and M-1 keys, so this is pretty much mandatory. The next rule is the keys in each node are in ascending order. Okay, now let's observe this particular node N1. Inside the N1 we have certain keys, we have 43, we have 65, we have 75. Are they in ascending order? Yes, we have small to large from left to right. Observe node N2, we have 25 and 40, again in ascending order. We have N4, again in ascending order, and also if you observe this entire level, that is also in proper ascending order, right? We have 25, 40, 50, 67, 70, 80, 88, 95. So completely in ascending order. Take a look at the last level also, all of them are in ascending order and individual nodes are also in ascending order. 28, 33, 45, 46, and then the whole entire level. So this is one property over here. So the next condition is the keys in the first I children are smaller than the ith key. Okay, so let's take a look at this node. We have 3 keys. Okay, so this is the first key, this is the second key, and this is the third key, correct, from left to right in ascending order. Let's take a look at 65. So I equals to 2 because it's the second key, right? Let's say I equals to 2. Now this rule is saying the keys in the first I children. So keys in the first I children means first 2 children. So for node N1, what are the first 2 children? These are the first 2 children, 2E and A3. 2E is nothing but N2. A3 is nothing but N3. So it's saying the keys in the first I children, that is keys. Keys means the values inside N2, that is 25 and 40 and 50 inside N3 are smaller than the ith key. So 25, 40, 50 are smaller than 65, correct? Makes sense? This is what this rule is saying. And this last rule is exactly opposite, that is key in the last m minus I children are larger than the ith key. Basically, you are saying the keys in the last 2 children is going to be larger than the 65 value, than the ith key. Okay? So if you see or if you observe this tree properly from a bird's eye view, what is happening is for 43 we have 2 pointers, and the first pointer can be considered as the left hand side. So 43 has a left hand side of node N2. 43 also has a right hand side which is N3. So values in the left side of 43 are smaller than 43. So 25 and 40 over here, correct? And values which are towards the right pointer of 43 are greater than 43 itself, which is 50. But for 65, that is the second key, this A3 is its left pointer. So since it is the left side of 65, it is smaller. So all values which are towards the left of 65 are going to be smaller, and it's not just going to apply to one level below. If you observe the children of 50, that is N8 and N9, both of them also have values which are smaller than 65, correct? But at the same time, all these values are greater than 43, because for 43, A3 is its right hand side or right pointer. So for every element or every key, you have a left pointer which points to a subtree which has smaller values. So for 75, X4, that is hash X4, is its left side or left pointer which points to this node N4 which has values 67 and 70. Both of them are smaller than 75. But hash Q2 is pointing to N5 which is towards the right of 75. So all the values inside this entire subtree has to be larger than 75. So you can observe 80, 88, 95, 76, 77, 79, all of them are larger than 75. And this rule applies to every node inside this entire multi-way search tree. So if you take this node also, these same rules are gonna get applied to this particular node N5. So for node N5, for this first element, hash Y7 is the left pointer, hash 98 is the right pointer, correct? So hash Y7 is pointing to this node which has values 76, 77, 79 which are smaller than 80. Hash 98 is right pointer of 80, so it should have values larger than 80. You can see 82, 85, correct? But hash 98 is left pointer to this second key, so it should have values smaller than 88, and you can see it satisfies that condition. 82 and 85 are smaller than 88, so on and so forth. So I hope you got these 4 rules which are extra on top of M-way tree, and this makes it a M-way search tree. Alright, so I hope you've understood what is a M-way tree, what is a M-way search tree, and lastly, just to clear out what a M-way tree and what a M-way search tree has different over a regular binary tree, that is what would be the advantage. Let me show you a diagram. So over here on the left hand side we have a binary search tree, and towards the right we have a M-way search tree. Okay, we have the same number of elements but we have different number of nodes, because in a binary search tree we can have only one value or one element or one key per node. But over here this is a M-way tree and this is a 3-way search tree. Okay, so since it is a 3-way search tree, M value is 3. The number of keys that it can store is going to be M-1. We just learned that, which means the number of keys per node can be 2. Hence you can see N1 has 2 elements or 2 keys, N2 has 2 keys, N3 has 2 keys and N4 has 2 keys, right? So that's the maximum it can hold. It can also have 1 key, but over here it is having 2 keys. So how many number of keys are there in total? We have 8 keys, correct? We have, let me write it down over here, 25, we have 19, we have 36, we have 14, we have 23, we have 28, we have 52, and we have 40. So now let's see in the binary search tree, if you want to access or if you want to find the value 40, so find 40, what do? You will start from the root node, of course. You will say 40 is of course greater than 25, you will come to N3, then it's greater than N3, that is the node value, that is 36. So you'll come over here, 40 is smaller than 52, so you will go to the left hand side of N7 and ultimately you will find 40 over here. So you can see the number of hops required were 3, right? So I'll write hops required is 3. Now if you had to find the same value 40 over here in the 3-way search tree, you would come over here 40, and of course in M-way search tree also we have similar rule where you will compare the number 40 with these two numbers, and of course when you realize 40 is greater than 36, in the algorithm itself you will know that you have to traverse to the right hand side of 36. So for 36, that is for the second key, these are the 2 pointers. So hash dd is the left pointer, hash z3 is the right pointer. Since 40 is greater than 36, you will go to the right pointer pointing to the right child, which is N4. Inside this node you have 40 over here itself, which is also arranged in ascending order. So immediately you get a match, and now you only required 1 hop compared to 3 hops in the binary search tree. Now this was just for example purpose and we saved 2 hops. If each hop was taking 1 second, we are just assuming, let's assume it was taking 1 second. In binary search tree, it would have taken 3 seconds to find the value. In M-way search tree, it would have taken 1 second. Now in reality, of course, this time will differ, because in this M-way search tree, when you reach this node, the 40 may be arranged at somewhere over here if the M value is large, right? If you have multiple keys, then you'll have to traverse this particular node also. So that will also take some extra time. But you save the traversal time itself, correct? Now in real world scenarios, this M value is very large, which means that the number of keys in one particular node is enormous and it's very high, okay? And that is done to keep the height of the tree short. You can see by comparing itself, this binary search tree is having a max height of 3, whereas this M-way tree is having a height of only 1, correct? So M-way search trees and multi-way trees in general are used in disk management and in algorithms where you want to access a particular node very fast and want to reduce the traversal time, okay? So this is just a representation and example to give you an understanding of how M-way tree has an advantage over binary trees, and that is the short height, fast access of nodes and less traversal overhead time. Okay, so this was the whole topic of M-way tree and M-way search tree. This was an introductory video. In further videos we will go in depth and we will try to understand more about multi-way trees, maybe even cover some types of M-way search tree like B tree and talk more in detail about them. But I'm gonna wrap up this video over here. I hope you've got the basic understanding of what is a multi-way tree, how it is different from binary tree, what is a M-way search tree and how it is different from binary search tree, and the analogy between the two. So hope you've understood this video. If you like this video, please give it a thumbs up. Let me know in the comments how this video was. Do share it with your friends and I'll see you guys in the next one. Peace.